Good morning, students. Today we will discuss vibrations of diatomic in one-dimensional lattice. In the last class, we saw about the vibration of a monoatomic in one-dimensional lattice. Monoatomic means there is only one atom. Diatomic means there are two atoms. So, consider a one-dimensional linear primitive lattice with a basis consisting of masses small m for one atom and capital M for another atom. This capital M will be greater than small m. These are placed alternatively along the x-axis with an interatomic distance equal to a. So instead of n, n plus 1, n plus 2, here we are representing 2n, 2n plus 1, 2n plus 2, etc. on the right side, and on the left side 2n minus 1, 2n minus 2, etc. Okay. Now this is the state of equilibrium and this is the state of displacement. Consider there is a 2n atom and here it is 2n plus 1 and here that is the capital mass, this is small mass 2n plus 2, then this is capital mass 2n plus 3, etc. Similarly, in this side there is a big mass 2n minus 1, small mass 2n minus 2, capital M 2n minus 3, etc. So alternatively we arranged the atoms. When there is a vibration taking place, this 2n position will change to this position, hence the amplitude will be x2n. In monoatomic it is xn, now it is x2n. In diatomic it is x2n. Similarly it is x2n plus 1. Here x2n plus 2. Here x2n plus 3, etc. Similarly in this case, in the left side, x2n minus 1, x2n minus 2, x2n minus 3, etc. So what we did in last class is similar here, but here there are two atoms. In that case there is only one atom. Here it is two atom. All procedures are same only. Now what will we calculate? F function, that force will be calculated. F2n, that should be is equal to m d square x2n by dt square. In the monoatomic it is d square xn by dt square. Here for two atoms, so this is represented as small m and this is for capital M. So d square x2n by dt square, that is equal to f into x2n plus 1 plus x2n minus 1 minus 2x2n. In the case of monoatomic it is x2n plus 1, xn plus 1 plus xn minus 1 minus 2xn. Okay, that is the difference, that's all. Then here x2n plus 1, this is for one atom, this is for another atom. This is different from monoatomic case. So here on excess case comes f2n plus 1, that is equal to capital M into d square x2n plus 1 divided by dt square, that is equal to f into x2n plus 2 plus x2n minus 2x2n plus 1. Here n is missing, it is a 2n plus 1. Okay, and f is the force constant. Similarly, what will be the solution? x2n, that is equal to a e power I omega t minus 2kNa. What in the case of monoatomic? xn is equal to a e power I omega t minus kNa. Here, since it is two atoms, here it comes 2kNa. Similarly, for x2n plus 1, this is for mass capital M, this is for mass small m, and this is mass for capital M. Therefore, capital B into E I power omega t minus 2n plus 1 Ka. Okay, so here two cases arises in the diatomic. In the case of monoatomic, there is only one case. Right. Now, where k is the wave vector for particular mode of vibration, It may be noted that the vibrational frequency of both atoms is assumed to be same. The vibrational frequency will be same, but the amplitude will differ. Amplitude will differ. A and B will differ because masses are different. For A the mass is small m, for B the mass is capital M. Capital M is somewhat greater than small m. Therefore, this difference of masses will create difference in the amplitudes. Writing similar equation for x2n minus 1 and x2n plus 2 and substitute these values in equation 2. In equation 1 we get the solution minus m omega square a, that is equal to f into b into e ika plus e minus ika minus 2fa. I solve this in the monoatomic case also. You just see that case. Similar will be arised here and similar derivation will be happened. Okay, this is for small. For capital M, minus m omega square b f of capital A e ika plus e minus ika minus 2fb. But we know that e ika plus e power minus ika, which is nothing but 2 cos ka. Therefore, you substitute 2 cos ka in this equation and it becomes 2f minus omega square m into capital A minus 2f cos ka capital B, that is equal to 0. 2f cos ka into A minus 2f minus omega square capital M into B equal to 0. The above equation is a homogeneous linear equation which give rise to non-zero solution for A and B. Therefore, you make the coefficients as determinant. So, 2f minus omega square m minus 2 cos ka plus 2f cos ka, this minus 2f minus omega square capital M, that is equal to 0. Now you multiply these two terms and you multiply these two terms, and when you solve it you will get minus 2f minus m omega square into 2f minus 2f minus m omega square plus இதை multiply பண்ணிங்கன்னா minus 4f square cos square ka. இதை minus பண்ணும்போது இது minus this, therefore this term become plus. Therefore 4f square cos square ka is equal to 0. You just multiply this 2f, that is minus 4f square, then minus of minus plus 2f small m omega square. Similarly for this term 2f capital M omega square, for these two when you are multiplying minus of minus plus into minus minus, therefore small m capital M omega power 4 plus 4f square cos square ka equal to 0. Here there is one minus 4f square, here one plus 4f square. Therefore, when you are taking out 4f square, minus 4f square is equal to 1 minus cos square ka, which is nothing but sin square ka, and divide throughout by m. You just solve it in the paper and you will understand this equation will come. Omega power 4 minus 2f m plus capital M divided by mm omega square minus 4f square sin square ka by small m capital M equal to 0. When you solve it, when you are multiply it, solve it, you will get this relation. Okay, right. Now the above equation is a quadratic equation in omega square, and the solution, and that is the root for that equation, is written as omega square, that is equal to f of 1 by small m plus 1 by capital M plus r minus f of 1 by m plus 1 by small m minus 4 sin square ka divided by small m capital M into whole power half. This is the dispersion relation for a linear diatomic atom in the lattice. Okay. For a monoatomic atom, we represent in the equation 7 in the previous equation, that answer will be omega square is equal to 4f by m sine square Ka by 2. This is for a monoatomic dispersion equation which was explained in the previous class. Now for dispersion relation for a linear diatomic in the one-dimensional lattice, this equation is there. But in the case of monoatomic, there is only one case arises, that is omega is equal to 4f by m whole power of sin Ka. So this is the only case arises in the monoatomic. But in the case of diatomic, there are two cases of omega. There are two cases of omega. What it will be? Because here we put plus or minus. Plus for one equation, minus for one equation. You see now, omega plus square, that is equal to, here you see plus for plus and for 1 for minus, f minus, this is f plus. Now consider for this omega plus. Omega plus means what will happen? The solution is when k becomes 0, sin Ka is negligible, therefore this value should become 0. So what will be the answer here? 2f will come, the same thing will come with root, because omega plus square is equal to this value. When omega plus means when you solve and take a root, it will be the answer. Therefore 2f 1 by m plus 1 by capital M whole power of. For k tending to pi by 2a, sin Ka becomes 1. Sin Ka becomes 1. When sin Ka becomes 1, this becomes 1 means this is the solution. Okay, are you understand? Here when k becomes 0, this term will be reduced. The solution will be omega plus is equal to 2f 1 by small m plus 1 by capital M whole power of. When k becomes pi by 2a, sin Ka becomes 1. When it becomes 1, you substitute here for 1. Therefore, the solution is this. Okay, alright. Now, when solve this equation, you will get omega plus is equal to 2f by m whole power half. 2f by m whole power half. Similarly, you consider for expression omega minus. The same thing will happen and you will solve this equation and you will get this thing. Using binomial theorem, you will get the answer like that. That is omega minus, that is equal to 2f by capital M whole power half for k tending to pi by 2a. This is k tending to 0. This is k tending to 0 and this is k tending to pi by 2a. Now, when you draw a graph, you will get like this. When you draw a graph, you will get like this. 2f by m whole power of, this is 2f by capital M whole power of, for this is for minus 2, k equal to 0 and this is k pi by 2a and this is k pi by minus pi by 2a. These are the two limits and you take the values from that equations. 2f by m capital half, 2f by m capital 2f by capital M into half, this is small m and here small m and here the capital M, and this is the value when k tending to 0. Here it is the k tending to 0 point. The allowed frequency range of propagation is split into two branches. Now, when in the case of diatomic there are two branches, in a monoatomic there is only one, like that 0, then 0 to pi by a, then pi by a to 2 pi by a, and 2 pi by a to 3 pi by a, like that. But in the case of diatomic, there are two branches occurs. One branch is called optical branch, another one is called acoustical branch. So one branch is called optical branch, another one is called acoustical branch. There exists a band of frequency between these two branches which is called as forbidden frequency. So when the vibration takes place, acoustic branch will occur, optical branch frequencies also occur, and in between these two another frequency will appear. It is called as forbidden frequency. When forbidden band is more, then the change of vibration will be different. It means that not possible to exist vibration in a lattice at a frequency which lies inside this band, and this band is called as forbidden band. When the frequency is between this value, then there will be no vibration will exist. There will be no vibration will exist in this band area. Maybe the vibration takes place in the acoustic band or in the optical band. The width of this band, forbidden band, will be depends upon the ratio capital M by small m. Larger the ratio m by m, greater is the width of the forbidden band. The existence of forbidden band is the characteristic feature of elastic waves in the case of diatomic lattice. If capital M equal to small m, then optical and acoustical branches coincides at k is equal to plus or minus pi by a, and the forbidden band will be disappear. So the main bandwidth of forbidden band will be due to the mass ratio capital M by small m. When the capital M by small m is greater, then the forbidden band gap is greater. When capital M and small m are equal masses, then these optical and acoustical branches will coincide at k is equal to plus or minus pi by a. Here we will also called a two-dimensional problem will be divided into or will be reduced to one-dimensional problem. Two-dimensional problem will be when capital M is equal to small m, then it will be the two body problem is reduced to one body problem also. We already study in classical mechanics, two body problem is reduced to one body problem. Similarly here, when m equal to m, then optical and acoustical branches coincides at k is equal to plus or minus pi by a. This plus or minus pi by a is nothing but Brillouin zone. We already study in the monoatomic atom also. The smallest possible wavelength of this zone is 4a. The smallest value wavelength of this first Brillouin zone is 4a, which corresponds to pi by 2a into epsilon. Pi by 2a into epsilon. The physical difference between the vibrations of the branches are calculated from the ratio of epsilon by eta at k tending to 0. Epsilon is nothing but the amplitude, the value occurs at optical branch. Eta is at the acoustic branch. When you are calculating the ratio between these two at k is equal to 0 for optical branch, when k becomes 0, the equation will become omega square by 2 beta epsilon minus eta divided by m1 epsilon. M1 is nothing but first atom, where this epsilon is called as coefficient of x2 n minus 1 equation, and eta is the coefficient for x2 n plus 2 equation. So when epsilon by eta, which is nothing but minus m2 by m1, minus m2 by m1. The above equation gives the masses moves in the opposite to each other and the amplitude being inversely proportional to the masses, and it is graphically represented as the motion will be one mass will be acting in this direction, another will be acting in this direction, one mass will act in this direction, another will. Then when you are seeing the amplitude circle, this mass amplitude will go like this and this mass amplitude will go like this. Okay, so there will be loop will arises. There will be loop arises. Okay, right. For acoustic branch, when this is the same relation, when k becomes 0, cos ka equal to 1 minus k square by 2. These are the coefficients x2n minus 1 and this is the 2n plus 2. You see here, when the ratio between epsilon divided by eta equal to 1, then all the masses will move in the same direction. All the masses will move in the same direction. Then the amplitude will be, this is for capital M, small m, capital M, small m, capital M, small m. Therefore, the circle, this amplitude will be a sine wave. Will be a sine wave or half loop. Are you understand the difference? On optical branch, you are getting a loop-like structure when you are connecting all the amplitude values. Here, when you are connecting, then it will shows a sinusoidal wave pattern. So this is acoustic branch. Okay, so this is what happens in a diatomic atom when it is placed in a one-dimensional lattice. The procedures are all same, but for monoatomic there will be no optical branch and acoustic branch, forbidden band, etc. But in the case of diatomic, there are acoustic branch, forbidden band, optical branch is possible. This is the difference between monoatomic and diatomic, but the solvation by mathematical procedures all are same only. You just see my notes and you just follow the things. Okay, right. Be safe and we will meet in the next class. If you have any doubt, you please ask in the comment section or in the WhatsApp. Okay, hope you are all following my lecture and you are reading well. Okay, thank you. Have a good day.